folks, welcome to another set of Chemistry 1 video notes. Today we'll be talking about the periodic table and electron configuration. By the end of this video, you should be able to write the full and noble gas electron configurations of an element, determine its number of valence electrons, and relate this to its position on the periodic table. You should also be able to use the periodic table as a model to predict the relative properties of elements based on their pattern of valence electrons and periodic trends. So let's talk about the chemistry of colors. You might notice after it rains, we often see a rainbow. Where did this light come from? Well, the sunlight, which we call white light, actually consists of all of the colors. When that light passes through a prism, like the mist in the air, it splits the white light into its separate colors, giving us a rainbow. On the 4th of July, you might wonder just how they get the fireworks to be such vibrant and different colors. Fireworks consist of two main components, a chemical compound and some type of explosive. The explosive serves to project the chemical compound into the air and to get the electrons inside of that chemical compound excited. Depending on the makeup of the compound, those electrons will emit different colors of light. For example, strontium nitrate makes red lights, barium nitrate makes green lights, and copper compounds make a bluish-green colored light. You might also wonder how they get neon lights to show such bright, beautiful colors. Neon lights are not made up of white light. They're made up of specific combinations of different colors of light. You don't get a rainbow when you put that light through a prism. You get a specific bands of color. This light is made in a similar way to the firework lights, but instead of explosives, we use electricity to excite the electrons in those atoms. To truly understand light, you have to understand waves. Electromagnetic waves are a certain type of wave with electrical and magnetic components. These waves are a form of energy known as radiant energy. The light we can see is one form of electromagnetic radiation. There are all sorts of other electromagnetic waves, such as radio waves, microwaves, X-rays, gamma rays, and ultraviolet waves. In a vacuum, these waves of energy move at 3.0 times 10 to the 8th meters per second. When the light travels through glass, water, etc., it slows down. This is why when you put a straw in a glass of water and you look down from the top of the glass, that straw looks like it's bent. That light slows down when it passes through the water, and when it comes back to your eyes, it looks like it's in a different spot because its speed changed. The length of a wave from crest to crest is called the wavelength, and it's usually measured in nanometers. The frequency of a wave is how many waves pass through a single point in 1 second. When we multiply the wavelength, this time we measure it in meters, by the frequency, measured in hertz or per seconds, we get the unit of meters per second, which gives us the speed of the wave. The speed of a wave is directly related to its energy. The faster the wave moves, the higher frequency or shorter wavelength, the more energy it has. The slower a wave moves, the lower frequency or the longer the wavelength, the less energy it has. The wavelengths are what make up the color of the light. For example, the higher energy violet light has a wavelength of 400 nanometers. The lower energy red light has a wavelength of 665 nanometers. Atoms are really good at absorbing only specific wavelengths of light. When white light hits an object, the light that doesn't get absorbed by that object's atoms is reflected back. That's the light that we see through our eyes. So for example, grass absorbs all of the colors of white light except green. It reflects that green light back to us, and that's why the grass looks green to us. Now, light waves aren't just waves, they're made up of particles called photons. To calculate the energy of a single photon, you have to multiply the wave's speed by Planck's constant, which is 6.626 times 10 to the negative 34 joules. Joules is a unit of energy. So at this point, you might be asking, what the heck does this all have to do with chemistry? Well, that's a great question. As we discussed, atoms will absorb energy. It's actually the electrons in the atoms that absorb that energy. and when those electrons absorb energy, they move further away from the nucleus. Eventually, they release that energy in the form of photons, or light, and they find their way back to their ground state, or closer to the nucleus. This animation here is a model of the hydrogen atom as Bohr imagined it. There's one single electron circling that nucleus. The electron gets hit with a light wave, and it increases energy, jumping to a higher energy level. When it jumps back down an energy level, it releases its energy in the form of a photon. The difference between those two energy levels will give us the energy of that photon. Thusly, it'll give us the wavelength and the color of that photon. If we look at the energy levels according to Bohr, they're pretty straightforward. We start at the bottom where n equals 1. If that electron gets excited to, say, the n equals 2 energy level, and then it falls back down, it'll release a photon that has the same amount of energy as the difference between n equals 2 and n equals 1. If the electron were excited all the way to n equals 3, it'd release a photon with even more energy as it jumps all the way back down to its ground state. Remember, the energy of a photon is inversely related to its wavelength. In other words, the more energy the photon has, the shorter its wavelength will be, giving you a color closer to blue or purple than to orange or red. As you may remember from our last video, the Bohr model is not actually the most accurate model. To be more accurate, we'd look at the quantum mechanical model, or Schrodinger's model. This model still has energy levels, like Bohr's. It has n equals 1, equals 2, etc., etc. But each of those principal energy levels has a sublevel, or a suborbital. These are called S, P, D, and F. The S suborbital exists in every principal energy level, starting with number 1 all the way to infinity. It is the lowest energy suborbital in each principal energy level. It is spherical shaped and can hold up to 2 electrons. These 2 electrons would spin in opposite directions, so we call one an up electron and the other one a down electron. The P suborbital is dumbbell shaped, starting with the second principal energy level, so it doesn't exist in the first. Every principal energy after that has p orbitals. There are 3 of these p orbitals, each residing on one of the 3 principal axes, x, y, and z. So we call them px, py, and pz. Each of these sublevels exist at the same amount of energy and can hold 2 electrons each. So just like the s orbital. At this energy level then, since we have 3 p orbitals, each holding 2 electrons, we would have a maximum of 6 electrons. The d suborbital is a bit more complex. There are 4 that look like a clover shape, and one of them looks like a p orbital with a donut around it. Only energy levels 3 and up have the d orbital. All 5 of these d orbitals are at the same level of energy and can hold up to 2 electrons each for a maximum of 10 electrons at that level of energy. Finally, our f suborbital, which is even more complicated, only exists in energy levels 4 and above. There are 7 of these f orbitals, each holding up to 2 electrons for a maximum of 14 electrons. Unlike in Bohr's model, where there are only principal energy levels, the quantum mechanical model has different sublevels within each principal energy level. For example, we have 2s, which is just slightly lower than the 2p energy levels. This separates the places that an electron can go even more, and helps us to better understand just what happens to electrons when they get excited. You might ask, well, how does all this come together? Well, there's something called an atomic emission spectrum. These spectra are like fingerprints for each element. Every single element on the periodic table has a unique atomic emission spectrum. Based on where the electrons exist on that energy level diagram we just saw, the electrons will have different levels of energy. When they get excited and go back down to the ground state, they emit very specific wavelengths of light. And when we look at that light through a spectroscope or a diffraction grating or even a prism, we can see those bands of light and identify which atom is being excited. So let's take this a bit further. We can describe an atom and its electrons by writing down its electron configuration. To do this, we take the number of electrons and fill in an orbital diagram, much like the one you see here. Each box on an orbital diagram represents one of the s, p, d, or f orbitals. Remember, the atomic number of an element is equal to the number of protons, and for atoms, it's equal to the number of electrons. So, here are our rules. We assume the atom is in its ground state, so we don't have any excited electrons that are out of place. We represent the electrons with up and down arrows and fill in the boxes. The Aufbau principle, named for a German word that means from the ground up, says that we have to start with the box at the lowest amount of energy and work our way up from there. Pauli's exclusion principle says that if we have more than one electron in a box, they must be spinning in opposite directions. In other words, we can't have two ups or two downs in one orbital. We have to have one up and one down. Finally, Hund's rule says that if we have multiple orbitals that exist at the same energy level, we have to place one up electron in each box before we can start pairing them with their down electrons. Basically, electrons don't like each other very much, so they try to spread out as much as they can before they have to start pairing up. So let's practice this. Our rules are written here on the left. Carbon has the atomic number 6, so an atom of carbon has 6 electrons. Filling in our arrows, we get one up and one down electron in the 1s orbital. We go one up and one down electron in the 2s orbital. And that leaves us with 2 more electrons to place. We would put these 2 electrons in the 2p orbitals, but remember, we can't pair them together because Hund's rule says we have to separate them if they can be. So we place one up arrow in each of the first 2p boxes. Now that wasn't so hard, was it? All right, let's try copper. Copper has an atomic number of 29, giving it 29 electrons if it's an atom. So let's watch what happens as we fill those in. You might notice the 4s orbital here is actually slightly lower in energy than the 3d orbital. That doesn't really make sense right off the bat because 4 is bigger than 3, so why doesn't it have more energy? Well, I'll talk more about it later, but the octet rule says that we can't have more than 8 electrons in our highest principal energy level. So in 3s and 3p, we've got 2 and 6 electrons respectively, giving us 8 electrons in the n equals 3 principal energy level. In order to place any more electrons in the third energy level, we have to place some in the next highest energy level, which would be 4, before we can go back to 3. That way we don't have more than 8 in our outermost energy level. Here's the problem though. Orbital diagrams are bulky and not a very efficient way to describe our electrons. They're nice to look at and help us understand how those electrons are paired or unpaired, but they're not very easy to write. A shorter way to describe our electrons is through electron configurations. We write down the principal energy level, so 1, 2, 3, etc., followed by its sub-level letter, which is S, P, D, or F, and then we put a superscript next to that sub-level letter that tells us how many electrons there are in that sub-level. So let's go back to our carbon example. To write out the electron configuration, we'd start at the bottom and write our principal energy level 1, followed by the sublevel S and a superscript 2 because there are 2 electrons in that orbital. Then we go to 2s2 and then 2p2. This is the electron configuration for carbon. For copper, we do the same thing. It'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d9. Before we hit the next segment of the notes, let's review some basics of the periodic table. Our horizontal rows are called periods. The vertical columns are called groups or families. Each element square contains an atomic number, an atomic mass, a chemical symbol, and the element's name. If we were to write out the electron configurations, we might notice a trend. For example, all of the elements in group 1 end in S1. All the elements in group 2 here end in S2. All of the elements in group 17 end in P5. This periodicity actually helps us name the groups and families on the periodic table. So group 1 is the alkali metals, group 2 is the alkaline earth metals, group 18 is the noble gases, 17 is the halogens, the big old chunk in the middle are our transition metals, and the 2 rows on the bottom that we pull out are the lanthanides and actinides. If you'll remember from 8th grade, the elements on the zigzag line are metalloids. To the left of that are all metals except hydrogen, and then to the right of the zigzag line are all nonmetals. The periodic table is actually way more organized than you might think. It's not just based on properties and the atomic number being put in order from 1 to 118. They're actually split into blocks based on the s, p, d, and f suborbitals. You can even use the periodic table to figure out the electron configuration of an element. The s block covers all of the group 1 and 2 elements and helium. The p block covers all of the group 13 through 18 elements, not helium. The d block is that rectangular chunk of transition metals in the middle. These are between groups 3 and 12. And then the f block is the section of the periodic table that we pull out, the lanthanides and actinides. If we follow the blocks from left to right, it gives us the electron configuration. So let's do that for carbon again. We hit 1s1 over here, we go to 1s2, 2s1, 2s2, 2p1, 2p2, giving us an electron configuration of 1s2, 2s2, 2p2. You might notice as we went down rows, that first number, the principal energy level number, corresponds with the row that the element is on. So for the 1s1 and 1s2, that's on the first row, it's the first period. For the 2s2s and the 2p45s, those are all in the second row, or the second period. We can do the same thing for copper. We get through the 1s2, then 2s2, 2p6, 3s2, 3p6, 4s2, and then we start on the d block. The d block goes down a number, so we go 3d and then 9. Sometimes writing that full electron configuration all out is kind of a pain in the neck. So we can use the periodic table to find the electron configuration, and then we can actually shorthand it even more by using the noble gas configuration. To do this, we write in brackets the noble gas that comes directly before the element we're looking at. So for example, if we're looking at bromine, we follow the periodic table back to the noble gas before bromine, which is argon. We then write the chemical symbol for argon in brackets, and then continue our electron configuration from there, giving us Ar, 4s2, 3d10, 4p5. This is a much shorter way to write the whole electron configuration, and it gets you the important part, which is the end, which is what we're going to look for next. Now I know this has been a long one, but I promise we're almost done, folks. Our elements are grouped with other elements of similar properties on the periodic table. For example, if we look at the valence electrons, or the numbers of electrons in the highest principal energy level, we notice a trend. Lithium, sodium, potassium, rubidium, they each have only one electron in their highest energy level, that S1 energy level. That means they have one valence electron. Same thing for our S2s and our P3s and our P4s. Just like we saw earlier, they end the same on the electron configuration. We use the electron configuration to figure out how many valence electrons there are. We go off those principal energy level numbers to figure out the outer shell. So if we have 4s2, 3d10, 4p5, that 4 level with the s and the p is our outer shell. Then we just count up the superscripts to find out how many valence electrons we have. The number of valence electrons will affect the reactivity of an atom. According to the octet rule, atoms want to have exactly 8 electrons. No more, no less. They can do this through gaining or losing electrons in chemical reactions. When an atom gains an electron, it has more electrons than protons, causing it to be a negatively charged ion, which we call an anion. When an atom loses an electron, it then has more protons than electrons, causing it to be a positively charged ion, which we call a cation. I remember this, even though I'm a dog person, but cats are cute too, so cats are positive, and that's why the positive ions are cations. Atoms that only have to gain or lose one electron are much more reactive than those that have to gain or lose more than one electron. Therefore, the elements on the top right of the periodic table and the bottom left are the most reactive. So on the left side of our periodic table, we've only got one valence electron, which is really easy to lose. It gets easier to lose that electron the further down the periodic table you go, because you're adding layers of electrons. And the further down you go, the bigger the atom gets. So the further away your electron, the negative charge, is from your positively charged nucleus. The further that is away, the easier it is to break off. So the atoms on the very bottom left of the table are very reactive. Same principle for the atoms on the top right of the table. So fluorine, for example, it has 7 valence electrons. It wants to gain 1 more. Since its atom is so much smaller than those on the bottom of the periodic table, it has a stronger positive attraction to gaining any extra electrons. The outer shell of electrons is closer to the nucleus, so it can attract it more. This makes it easier and more reactive for a fluorine atom to go through a chemical reaction than chlorine or bromine or iodine. On the very far right of the table, we have the noble gases, which already have 8 electrons, except helium only has 2, but its outer shell is completely full. They don't want to lose or gain any, so they're completely unreactive. The ionization energy is the amount of energy it takes to remove an electron from an atom. Remember, atoms at the top right of the periodic table want to gain an electron. They have 7 valence electrons and only want to gain 1 more. So to take away one of those electrons would take a lot of energy. It takes more energy to lose an electron the further up and right, or closer to the nucleus, and more valence electrons in one shell we go on the periodic table. Electron affinity is actually basically the same trend. This is how much an atom wants to gain an electron. Fluorine has the most electron affinity. It's the smallest atom that has 7 electrons, and it just wants to gain that 1 more. The atoms on the bottom left of the periodic table, they don't want any more electrons. It doesn't make sense. They want to lose an electron. So their electron affinity is much smaller than the ones on the top right. And finally, we get to atomic size, also known as atomic radius. The further down we go on the periodic table, the bigger the atom is, because we're adding layers of electrons. However, as we move to the right, we're staying on the same level of electrons, but we're adding more to that outer shell, which adds a larger amount of negative charges, which can attract the nucleus even more. So with more forces attracting between the outer shell and the middle of the atom, they kind of scrunch in together, and the atoms get smaller as you go to the right. With this knowledge on the trends of the periodic table, you should be able to compare the properties of any 2 atoms that you see on the periodic table based on where they're located, and based on how many valence electrons they have. Well, finally, folks, that's it for this set of notes. I hope you were able to get through them with relative ease, and you're able to take away the information you need to complete the tasks in your 2 standards. See you next time.